Hey there folks, and welcome to another edition in the Physical Geology 101 video series. I'm Geology Professor Shawn Willsey. Thanks for joining me. Here in episode 26, we are going to look at folds and basically the manifestation of ductile deformation. What happens to rocks when they bend without breaking? How do we describe the different structures and geometries? How does it all work? We'll put some of that together. Again, thanks for joining me. This is a video series based on my Geology 101 course here at the college. So it's all the same content, everything you would get if you were actually sitting there in class. So thanks for being a part of this. So we've covered several aspects of rock deformation. We've looked at how to measure strike and dip. And to round out this unit on rock deformation, we're going to look at folds today. And then in the next episode, I guess that'll really round it out. We'll look at faults, the manifestation of brittle deformation. And I've got myself kind of big on the screen here because I'm going to use a couple of props here to get us going, and then I'll shrink myself down a bit. So let's remember that folds consist of two limbs and an axis. So if I take my fold here, let's see how we could do this here. You can see there's two limbs, the sides of the fold. That's where my hands rest. And then up here at the tippy top, this is the axis. This is where the fold changes direction. So we can have geometries such as this that help us describe folds, limbs and axes. Now, folds can have a variety of shapes. They can be symmetric, like the fold I have here. Looks like a nice happy rainbow. But they can also be asymmetric with a steeper limb and maybe one gentle limb. They can be upright. So if we take these rocks here and say that the yellow layer of foam is the oldest on the bottom, the blue layer is younger, so it's on top. And we can have this fold be upright, so still yellow's on the bottom, it's the oldest, blue's on top. Or we can actually have folds completely invert and either invert one side of the fold, like where my hand is touching here, notice the yellow layer is on top. Or you can rotate the entire fold over such that now the yellow layer, the entire yellow layer is on the top. So upright versus overturned. The angle or I suppose the openness of the fold can vary from very broad, barely folded structures like this to very tight folds. We sometimes call this isoclinal, fancy term, but very tight fold. And then the last thing here, I might use something a little different, maybe my manual to show this one. We can have folds that are horizontal, meaning the axis here is horizontal, or it can actually be plunging. So we can have the fold axis be in a horizontal plane, or it can actually be diving down into the ground in any given direction. And this is what we call a plunging fold. So hopefully the props there helped a little bit. I'll go ahead and shrink myself back down a bit. And so the main types of folds we're going to explore here with this video are anticlines, synclines, and monoclines. And everything you need to know is in the prefix here. Anti meaning opposite or opposed. Syn, S-Y-N, not S-I-N, meaning together or with. And then mono, of course, meaning one. So let's start with an anticline. And for each one of these, we'll have a simple cross-section that'll help us understand exactly what's going on with this fold. So let's start with a sequence of 4 layered rocks, yellow on the bottom, pink, green, and then blue on the very top. And we'll go ahead and to form this anticline, we're going to compress the rock. So we'll exert a compressive stress. The rocks are being squeezed in a vise, if you will. And that stress will deform the rocks. And in this case, we'll arch them into a fold that has this sort of geometry. And then if we allow for the effects of erosion to take place after the fact, we might end up with something like this. So a few takeaways with anticlines then. The thing that really defines an anticline is that in the center of the fold, we have the oldest rocks. Notice down here in the center of the fold, we have that yellow layer, which is our oldest layer in this case. The rocks are arched upwards. In this case, they're kind of making a rainbow shape. And the limbs dip away from the center. So on each side of the axis, the limbs are dipping opposite or away from the axis of the fold, hence the term anticline. So this is one type of fold we have in geology, and as you become proficient with these terms, you'll start to see them more often as you start to recognize these structures. Let's look at the opposite sequence with the syncline. Let's start with the same 4 layers, yellow to blue, oldest to youngest. Again, we're going to apply a compressive stress to these rocks, but instead of the rocks arching upwards, we're going to do the opposite. And now the rocks are going to be arched downwards, forming a bit, I guess, a smiley face or a half pipe, depending on what your preference there is. Notice now the yellow rock's still at the bottom, so superposition is still valid. Blue rock's on top. And then if we allow erosion to attack these rocks, we might end up with something like this. Looks really similar here. And notice now the important thing that defines a syncline is that we have the youngest rocks in the center. So we go to the center of the fold where the curvature is bending around the rocks, we find the blue rocks, and those of course are younger than the rocks that are adjacent to them. So the rocks are arched downward, the limbs are dipping towards the center. Notice this green limb here is dipping to the right on this side. Over here, it's dipping to the left. And so these two sides of the fold are dipping towards the center or towards the axis of the fold. So there are our anticlines and synclines, two basic structures in geology. I thought it would be fun to look at an actual example. So I took a Google Earth image from the Lost River Range here in Idaho, which shows a fantastic anticline-syncline pair. So here's Bora Peak over here. This is the tallest point in Idaho. All these gray and beige colored rocks that you see here are sedimentary rocks, mostly limestones, a little bit of sandstone from when this part of Idaho was underwater, was under the ocean. They were later deformed during the severe orogeny. So these rocks were squeezed, compressed, and folded into this beautiful anticline-syncline pair that you can see right here in the center image here. And then later, much later, these rocks were uplifted by basin and range extension and brought to the lofty heights that we see them at today. But a great example of the folding we see in these bedded sedimentary rocks, anticline-syncline pair. So our last fold that we'll look at is what's called a monocline. Monoclines are a little bit different. Maybe I'll go back to my, blow myself up a little bit bigger and show you what a monocline might look like with the foam. So in this case, we're going to deform the rock, and we're going to have two sections where my hands are sitting that are horizontal, and then there's just one limb. There's only one section of this fold that has a tilted angle or a dip to it, and that's why it's a monocline. So it's essentially like a ramp or a step. The rocks are still right side up. There's no, rocks have not been flipped over in this case with this monocline. And monoclines can be, very broad and quite gentle, like this one here, or you can make them much more extreme. And at this point, as we sort of rotate that limb past vertical, now we do have overturned rocks in this case. And depending on which side you're looking at this might look like a Z or an S, depending on which side you look at it from. If I go the other way, it's going to look like the opposite letter, S or Z. So these are monoclines. These are often formed by compression, but you can get them as well formed by tension. Basically, these rocks might behave more ductily at the surface before they actually break. And usually there's an underlying fault that's responsible for monoclines. We won't spend a ton of time with monoclines, but they're pretty cool. They're worth noting. Some areas like in the Colorado Plateau region of southern Utah, northern Arizona, there's some classic examples. They're really interesting and dramatic landform features. And I'll show you one such one here. This is a photograph of the Gray Mountain monocline. This is at the east end of the Grand Canyon region on the south rim. So you can see the rocks here are horizontal, but then you can see them bend down. That's that one limb that defines the monocline. And then as we come here into the foreground here, we can see the rocks are horizontal again. So they're horizontal, they ramp up, and then they're up there on the skyline. And this is one way you can get the same layer at two very different elevations in some region, is to have these monocline structures there. Okay, so let's put this together and start applying it in a little bit more detail. So now that we understand anticlines and synclines in particular, we should have the skills then to identify these folds in geologic maps. And so in map view, looking down on the ground, first of all, if these are a bunch of rocks, remember we're looking at the ground now, we're not looking at the cross-section view, we're looking down from above, we're in map view. And let's say someone's gone across this landscape and mapped out a whole sequence of rocks, and we can see that each rock has its own color. So how do we know these rocks are actually folded? Well, if you notice, there's repetition, right? there's only 4 rocks here, yellow, blue, pink, and green, only 4 rock layers present. But we do see repetition as we move across this landscape from left to right. We go from pink to yellow to blue, but then back to yellow and to pink. And so there's repetition here. So by finding the areas where the repetition occurs, those centers, that's defining the axis of these folds. And so as we work across this landscape, we might identify how many folds are here. We can also add, if we're doing real geology on the ground, we can also add strike and dip symbols. Remember, we learned about these in a previous episode. And so these dip symbols now really define exactly what's going on. You should be able to tell an anticline from a syncline in map view, either by the presence of these strike and dip symbols, which are featured on geologic maps, or alternatively, you can also identify those folds by looking at the age relationships at the structures. And I'll show you that here in a second. So in this case, notice we've got the blue layer has yellow repeated on either side. So we know that this is the axis of one fold. As we move across, there's another repetition with the pink layer, yellow on each side. Then there's again repetition on the blue layer. So it's repeated again. Okay. And then we go yellow, pink, green. So green would be the next axis. And then we go pink, yellow, blue. So it looks like we have 1, 2, 3, 4 fold axes present in this view. We can tell what kind of fold it is by looking at our strike and dip symbols. Remember, the long line of our strike and dip symbol designates the strike. And in this case, the strike should always be parallel to the contacts, the lines between the different units in map view. But the little dip symbol here, the little smaller line attached to the strike and dip symbol, this is the one that's most instructive. Notice over here on this first fold, the blue one here on the left, that we have the dips facing inwards towards each other. So if the dips are going to go towards each other, think about what kind of structure that is. Hold your hands up and hold your hands so that they dip down and touch the other one. What you've just done is created a syncline geometry. So we have a syncline over there. If we come over here to the next axis of the next fold, here the pink layer, notice that the dips are opposite. So now we would hold our hands up and maybe kind of make like a little rooftop with our hands dipping away from the point that they're touching, away from the axis. So that would be an anticline. And then there's another, you guessed it, syncline right here where this wide blue zone is. And then our final fold over here is another anticline. So in cross section, what would this look like? Well, it would look something like this. There's our syncline, anticline, syncline, anticline. So we actually have 4 individual folds, 2 synclines, 2 anticlines. And so we have a fold train, if you will, a whole series of folds across this region. And so this cross section perfectly shows the 3rd dimensional view of what the map would show. But you should be able to, and this is where geology is a 3-dimensional science, you should be able to take this map information and then project into the ground what that cross-section would look like. And this is something geologists do all the time. They go out and map the geology on the surface, then they construct a cross-section to help display or convey what that geology looks like in this type of view here. So hopefully that's helpful there. So we actually have a series of anticlines and synclines there. Let's look at this pattern here. This is a fold in Wyoming. And the thing I want you to notice here is it's a little bit different than the last one. Remember that the contact lines here in our last slide ran straight across the map. They were all running, in this case, I suppose, north-south, if north is up, across the map. All the strikes were north-south. But now as we look at this fold, notice that there's a continuation of these rock units that defines a bit of a V or a U shape on the ground. So you might be able to tell what kind of fold this is. This, you can see the rock layers over here are steeply dipping down to the left. A little hard to tell on the other side, but the rocks here are dipping off to the right. And so this is another anticline. But what makes this one different is this nose of the fold here. This is what we would call a plunging fold. So this is a plunging anticline. I'll try to show you with the notebook here. That's actually diving into the ground. So it's diving in towards your view there. So it's not a horizontal fold or a non-plunging fold. It's actually a plunging fold. And you can distinguish plunging folds from non-plunging folds by looking at the pattern they make in cross-section view. Let me take you real quick to a fun little tool, and I'll put a link for this in the video description. They've changed it a little bit. I used to be very familiar with this is Visible Geology, but some other companies bought it up. They've tweaked it. I think it's better, but it's I haven't played with it enough to become proficient with it. So what we have here is a three-dimensional block that we can rotate around. So notice that if we look at it from the side, if we look at it from this side, we can see the layers: purple, green, light green, blue, yellow, kind of pink. So we can see the superposition. If we rotate it to the other side, we can see the fold itself. So in this case, it's a nice anticline. And then if we rotate to the top view, notice, or map view, notice we can see the contact lines. So it's just like those slides I was showing you where you're looking for the repetition. This dark blue layer has the light blue repeated on either side of it. So I know there's a fold there. I don't know what kind of fold it is until I either get those strike and dip measurements, or I know the age relationships, or in this case, I can see the side view, so I know it's an anticline. But the point here is that in a non-plunging fold, the contacts are parallel and straight. So here's an example of a non-plunging anticline. I've also queued up a non-plunging syncline for you. So again, in map view, looking at the top view, notice that the contacts are straight and parallel. We can see where the repetition is. The orange unit is repeated around this middle layer, kind of light colored. And then if we go to the side views, we can see what kind of structure it is. We can see it's a syncline. If we rotate to this side, that's the side view. So it's hard to tell what kind of structure it is, but we can see at least the order in which the units were deposited. So here's our non-plunging folds, a non-plunging syncline. And here's what the plunging folds look like. So let's start with the cross-section view. Again, this looks just like an anticline, okay, the arched upwards. If we go to the side view though, remember on the other one that they were horizontal, but here we can see they're tilted. That shows us the direction that the fold is plunging. It's plunging to the left in this case, downward in that direction. And because it's plunging, when it's all eroded on the landscape, which is flat in this case on this three-dimensional box, notice that it makes a V shape. So that pattern of the rock units, the contacts, makes a bit of a V shape. On this one, they've actually added fun little strike and dip symbols as well. But this gives you an idea of what these structures look like in 3 dimensions. So you can see the full structure here, the top view and the sides view. So we have a nice plunging anticline here. And then to round out this little sequence, let's check out a plunging syncline. Again, we'll start with the side view. Okay, so that lets us know it's a syncline. If we rotate 90 degrees to the side, we can see that it's plunging. The rock units are not horizontal, but they have a dip to them. So these planes of rock are dipping. And because they're dipping and they're folded, that makes the outcrop pattern have this sort of V shape to it. They use kind of a funky color here, but you can see this yellow layer here kind of defining the V shape, and then the green coming through like this. And again, they put strike and dip symbols on here as well. So a nice example of a plunging syncline. So non-plunging and plunging folds, mainly again sticking with this anticline syncline game. One or two other things, and then we'll wrap up, and we'll do a little quiz question here at the end, of course. One final thing is you might ask yourself, well, what does a fold look like if it's laying on its side? So here's one from Death Valley. So instead of being an anticline or a syncline, what if the fold actually gets deformed and it's sort of laying on its side or C-shaped? And these are called recumbent folds. These recumbent folds can actually be either anticlines or synclines. I don't know which one this one is because I don't know the age of the units there. But if we start with my little webcam here and go yellow on the bottom, blue on top, and we deform it and then rotate it into a recumbent fold, you should be able to tell what kind of fold it is because the yellow is in the center of the fold, and the yellow was the oldest layer. So this is a recumbent anticline. If we take the same beginning situation, yellow on bottom, blue on top, yellow's the oldest, and we fold it into this sort of shape, notice the blue is in the center of the fold, and this then would be a recumbent syncline. So I've given you a lot to chew on here, team, but I think the main thing to focus on are anticlines and synclines, being able to identify them just by shape. That's good. But then as you get a little bit more proficient and maybe start looking at geologic maps, you can start to identify them using strike and dip symbols or age relationships. So let's go right to our quiz question. So let me walk you through this a little bit and then let you have at it. So what we have here is a map pattern of rocks. So I've listed the different rock types here on the map. In parentheses, I have the age of the rocks, which is shown over here in the bottom left corner. Triassic is the oldest unit, then Jurassic, Cretaceous, Paleogene. So these are organized from oldest to youngest. So you have the ages of the rocks, and you can see the outcrop pattern here. So your job here is to pick how many folds are present on this map and what their centers are with respect to these yellow letters. So you're going to identify not just how many folds there are, but where they're located. So go ahead and pause the video if you need to think about that a little bit. Alrighty, let's go ahead and have at it. So let's see here. Let's just work our way across this landscape and look for a fold. How do we know there's going to be a fold at all? Why can't these just all be tilted on end? Well, if they were just tilted like a bunch of dominoes, they would get older or younger in any direction. You would just go one layer, one layer, one layer, right? But when we look for repetition, that tells us there's been folding. So as we work across this landscape, from the breccia to the sandstone, from Cretaceous to Jurassic rocks, the rocks are getting older. Then I go to the limestone, the rocks are getting older. Then I go from the limestone to the sandstone. I'm repeating that same sandstone, and the rocks now are getting younger. So that tells me I have a fold. And in this case, it's centered on X on that Triassic limestone. Do I have another fold? Let's see. Let's keep moving across the landscape. I go from the limestone to the sandstone. Rocks are getting younger. Sandstone to the breccia. Rocks are getting younger. Breccia to the shale. Rocks are getting younger. Shale to the breccia. Rocks are getting older. So again, I'm repeating that breccia unit around the shale. So my second fold axis is located right here on this Paleogene shale, or letter Y. So we have two folds centered on X and Y. A was the correct answer. So if you did okay on that one, great. If you didn't, that's all right. The next question you might have, so here's our follow-up quiz question, is, well, okay, now I know where the folds are, but what kind of fold are they? So we know there's a fold here. We know there's a fold here. So what kind of folds do we have? So go ahead and pause the video if you need a second to work on that. Okay, let's go ahead and tackle this one. So what we have here, again, is we want to look at age relationships. No strike and dip symbols given to you this time. That's one way to identify folds, but you can also do it with age relationships. So in this case, if I go to the axis or the center of the fold, I see that I have the oldest rocks, that Triassic limestone with younger rocks around it. Therefore, X would have to be an anticline, oldest rocks in the center. I go to Y, Paleogene shale is where the axis of the fold is. It's surrounded by older rocks, so I have youngest rocks in the center. That would define a syncline. So X is an anticline, Y is a syncline. Looks like that was answer C. You might ask yourself, well, what would this look like in cross-section? So I've actually gone ahead and recreated the map view here, and then what the cross-section would look like. We have an anticline-syncline pair. And so the utility of this might be all sorts of things. Oil and gas industry, we might be looking for structural traps, like in an anticline where the oil or natural gas gets trapped beneath less permeable units. So by knowing where these folds are and what kinds of folds they are, that might dictate where we drill for this resource. All sorts of reasons why this strike and dip and fold identification thing is super important. So hopefully that was helpful to you. Kind of a long-winded episode, lots to digest here with folds. What we'll do in our next episode is we'll break down faults and how we identify different types of faults. So we'll see you next time. Thanks for your support of the channel. Hope you're enjoying this series, and be well.